Good evening. Welcome to the 25th session of Astro Adda, where we have eminent astronomers from the Astronomical Society of India coming and giving popular talks, but with also flavor of quantitative flavor possible for students to take up, organized in collaboration between the Nehru Planetarium, Nehru Memorial Museum Library, New Delhi, and the Astronomical Society of India. We are, in fact, today very, very fortunate. Today is the first time probably we are going higher in energies than X-ray astronomy. And we are fortunate to have senior most, very, very experienced astronomer, Professor Palahalli Vishwanath, who has had about 23 years experience from the Tata Institute of Fundamental Research in High Energy Astronomy and later at the Indian Institute of Astrophysics. And in these high energy astronomy endeavors, he has had experience going deep down into Earth and going high up on mountains to access information related to high energy astronomy. Professor Vishwanath, we are very grateful to you that you have offered to bring youngsters up to date on this field and Indian endeavors. I will ask you to come in. I'm just going to add your presentation into the stream, and so your presentation is now visible, full screen, and so I will hand over to you.
Uh, Thank you very much, Dr. Ratnashree, also the people connected with the Nehru Planetarium and other organizations. And today my talk would be experimental high energy astrophysics. Now, this is a public talk, so I will try to keep the technical part to as much to a minimum as possible, though I would probably have to stress uh, some technical details here and there. And so I'm going to take you through this experiments through the field of different aspects of high energy astrophysics. What does this experimental etc. mean? You see, study of the highest energy particles in the universe is what we do here in these fields. And of course, study the celestial sources which generate them, how they generate them. These are our these are the questions we ask. So when we do this, we actually are extending traditional astronomy, that is, optical astronomy, etc., to higher energies. That's what we really do when we do this. And another interesting thing here is why we do it, and which I will stress probably a little later, is some objects are probably seen only in high energy. So if you don't do high energy astronomy and astrophysics, you will never know about them. So that is what we want to do. And the plan of my talk is given here, and I will start with an introduction. Crab, Crab Nebula, Crab Pulsar. Actually, it's going to be our reference point for throughout the lecture, and I'll soon introduce you to this very interesting object in the sky. So once we do that, we'll go to X-rays, and these are different aspects of high energy astrophysics. X-ray astronomy, low energy gamma rays. These are done with essentially with satellites and maybe balloons to some extent, and very high energy and ultra high energy. These are all names there, essentially different techniques there. It's all gamma rays. These are ground-based studies, and cosmic rays, of course, we got to talk about, and if we do have time, a little about neutrino astronomy. So let us go further. Now, first we'll try to understand what a supernova is. I would, as I said very initially, the thing is it's a public talk, and please, experts, bear with me. and because you probably know all this, and maybe you know this better than me. And for example, you see the left part of the sky here, left part of the thing here. There's nothing in the sky, and then there is all of a sudden there's a very bright star. This was actually what we call supernova 87A. Number is missing over here. And February 23rd, 87, that is 34 years ago, we had this anniversary just this week. And all of a sudden, this bright object appeared in the sky. Okay. And then they went back because they had data and they looked, well, there's nothing there. So what happened really was some star here uh, kind of all of a sudden flared. We'll see why. And we have this object called a supernova. And initially, it's rather innocuous patch in the sky. And this was actually the first supernova of modern times, when we had all the telescopes, etc. And so it has been very well studied. Lots of theories of supernovae have been verified with this object. I probably won't say much more about this object later. But now we go back by 900 years or something, and we go to 1054 and July 4th. July 4th is American Independence Day. And, at that time, the Chinese astronomers, you want to call astrologers, whatever, they were always keeping a track of what happens in the sky. And some other civilizations too, Koreans did, Japanese and Native Americans. They recorded, just like here, appearance of a new star. They give a lot of details, actually very interesting to go through those things. And they call them guest stars, and in Kannada or Sanskrit we call them Atithi Nakshatra. And uh, so this was a new guest star. It was there for a few months. It is very bright, I think as much as almost like Venus. And it seems it was bright enough to be seen during the day. All right, this was 900 years ago. And do we know anything about it today? So let's go to the next slide. And we come to 18th century. Actually, it should be 18th, I think. And there's an astronomer, well-known astronomer called Charles Messier. He was looking at various things in the sky. He had a good telescope, and he recorded the fuzzy ball, and he called it M1. And somebody later thought it looked like crab, and that's the Crab Nebula. So only with time we realized that what the Chinese saw in 1054 has really become like this, what we call a Crab supernova event, or another this thing is Crab Nebula. This you can see the left part of the here, a very beautiful object really, and this was taken by Hubble with a lot of exposures, and I'm told here it's one of the largest images taken by Hubble, and is the highest resolution. So here different elements start for different elements, etc., etc. Okay, now uh, so we have the Crab Nebula here, and it slowly became a very important source in astrophysics. And we also call it the Rosetta Stone. Rosetta Stone, as you know, was used a long time ago to decipher Egyptian uh, hieroglyphs. And this is the first, as we have seen already, first object with a historical supernova. Today, of course, you cannot see it with naked eye, but naked eye can go to 6 magnitudes, but this is something like 8, and with a good binoculars, we can see it very well. Now we will know a little more and more about the physics and much more detail. These are still qualitative. All right. Now this is the optical. That means you do it with a telescope. All right, the optical telescope. Okay. Now the question is this, which we did answer immediately around when we found it as a nebula or supernova remnant. Only later. How does this nebula shine really? I mean, how does it uh, give out any light? Because as we know, it's not a star. If it's a star, it would have thermonuclear fusion reactions and eventually light comes out. But here nebula is cold. So there got to be some other mechanism to give you optical light here. Optical, and as we see later, radio, etc. This is something called synchrotron radiation, very uh, uh, favorite mechanism for most of these processes. And what happens is essentially a charged particle, the electron plus, and uh, when they go through magnetic fields, they generate these photons. Okay. Now, what we want to do is, of course, we have seen Crab in optical, so we want to look at some other things. Let's see some other electromagnetic spectrum. So in 40s and 50s, they asked this question. The only other window which was available was radio, which had been opened by Karl Jansky and others in mid 1933 plus. And so this is what we see here. This is how radio maps see, and of course, when you increase the light image of that. So of course, in 50s we came to know, as I said, it's due to synchrotron radiation. But we have still got to answer one question here. We keep saying fast charged particle with magnetic field. But who is making these charged particles? What is the source of these particles? That we'll see only later. 1950s is still too early for that. So, but now we're not just happy with radio. We want to see something else. Now, this is the electromagnetic spectrum. Most of you may be familiar with this. It starts with the radios here at low energies. I will use the word energy. I'm not a high energy person. I would not use wavelength and things like that. So this is the lowest energy here. Highest energies are gamma rays, X-rays, etc. This is the visible light. So we have already seen these things in the lab in 1900, let us say, and all these will know. But do we see it from the sky too? And so that was the question. And I will like to familiarize you with some of the units here of energy. As you know, Einstein said photons, light is consist of particles called photons. So in particle terminology here, we say 1 electron volt is what an optical light has. Oh, this is just ballpark, just to remember. That's the energy just your ordinary light has. But when you come up to X-rays, 1,000 times higher, kilo, gamma, billion times, much more than that. And to keep a reference, proton mass is 1,000 G, 1,000 electron volts, about a GeV. And something called top quark is much, much higher, the highest we know at the moment. Okay. So we want to see Crab in all this. That's what our aim is. So, well, okay, we want to see, but does nature oblige us? Well, not really. You see, this is the atmospheric uh, transparency. That means can the light come down to us? Like visible light here, you can see this comes down and there's a telescope sitting beautifully. Okay, atmosphere is transparent to that. Same thing with radio. That's how these things could start much earlier. But if we go to infrared or let's say X-rays, you see, no, they get absorbed. They don't come down the sky, come down in the atmosphere here. But gamma rays, as you will see later, will eventually come down, but that's later. So we got to go up with the atmosphere if we really want to look at X-rays. But in 1950s, of course, we were not ready for that, but 1960s we were. So these are the high energy astronomies, and I think I already spelled out each one of them for you. And the reason why we have these different names are essentially because low energy, high energy, etc. Techniques become different. That's the basic thing. And one ought to remember here that most of these instrumentation was really used from the cosmic ray experiments in the early days. Today also in high energy physics, quite a few where it's all that type of instrumentation. Not you're probably familiar with optical radio type of thing. Okay, so X-ray astronomy has to be opened up. It had to wait for the space age, uh, then the so-called these rockets, sounding rockets, which was there in the went up and stayed up for a few minutes. They were used, and as I said, there is this person called Rossi, who's a great cosmic ray physicist, and later he is the founder of X-ray astronomy. X-ray astronomy got a Nobel Prize later, but unfortunately he was not alive at that time. And the detectors are essentially uh, thin counters, GM counters, bigger Bowler counters. And that means traditional cosmic ray thing. So Rossi set it up in the sky, in the sounding rocket, and he was lucky. This is Professor Rossi, this associate. So those are the counters. Very simple instrumentation. But they were very lucky, really. First time they somehow got the brightest X-ray source called SCO X-1, SCO stands for Scorpius constellation. And these are the number of photons or counts, let's say. These are from background, and it's very high. This is the SCO X-1, a brilliant this thing. So they found SCO X-1, and of course, our we keep asking this question. As I said, how does how does do we get scrap in X-ray? Okay, they found it, and it's not too much different, and but we'll see much better picture this time. This is the crab in X-rays. So X-ray astronomy took off in the mid 60s, early in the mid 60s. Now, this is just a little bit slight technical issue, but I think one got to familiarize oneself with it. This is called an ionization chamber, mother of all detectors. You know, in the late 18th and early 19th century, so they started using these things, and essentially a charged particle comes, ionizes. There will be gas in this, and uh, then you get a signal here. So this is the basic thing. Because it's all very complicated later. This is from this we get GM counters, proportional counters, different voltages, etc. And this is, for example, when a particle passes through, you get the track. And X-rays, you know, as you probably know, if you cannot just use a optical mirror like a spherical mirror sitting on that because it gets absorbed. So X-rays, if you want to see, you got to use these mirrors here, which are called uh, actually grazing type of thing, or grazing incident. You just smoothly come in, go back, go here to the focal point. This is used for low energy X-rays. The high energy X-rays, etc., we use detectors. Okay, what happened? No, X-ray sky opened up. I just want to show you the differences. See, this is the optical sky around Orion, which some of you may know, the beautiful region in the sky in the winters. And here is the Orion Nebula, etc. The famous stars around. This is actually Sirius X Sirius, the brightest star. I think this is Moon. So what happens? It's the same thing in X-ray. And well, many things are seen. We don't even know what these are. And another interesting thing which happens is Sirius by itself is of course bright in optical, but it's not all that bright in X-ray. What shows up here is what's called Sirius B, which is what's called a white dwarf. So different things open up. As this is what we wanted to point out, that in a different electromagnetic window, you see different things. Here is Saturn, our nice optical. This is what looks like X-ray. Okay, now I'm not going to go through all the X-ray sources, etc. This is a very review type of talk here. So, what has happened in the last 30, 40 years? Actually, the number of years is much more. This is a sky map, like, just like our latitude, longitude for Earth, uh, latitude or longitude. Similarly, this is called galactic latitude or longitude. Initially, what a satellite called Uhuru. Uhuru means freedom, I think, uh, in Swahili. And so many. sources were found. But this is one of the latest called ROSAT. You can't even know. There are many stars, we many X-rays objects now. Plenty, a lakh plus. Okay. So that's X-ray astronomy now. And I'll of course tell you slightly more, but I'll take a detour now and talk about something called pulsars, which again, as I kept saying, some of you know. And here is a young lady, Jocelyn Bell, a graduate student at that time in the mid 60s in Cambridge, and with the Jodrell Bank new array, they started looking at sky. And this she found after, this is a chart recorder type of thing. I don't know how familiar you are with chart recorders. Like if you go to electricity offices, you may still find some like that. So she found, and you can see here very regular pulses here. It took a lot of effort for her, and so this is what which we call a signature of a pulsar. It has got a particular name. Let's not worry about that. So Jocelyn Bell essentially discovered pulsars in 67. As far as this shows, this is an object which gives out a very regular pulses. These are called pulses. And what are these? These are compact objects which we did not know initially. These came later. What we initially do was just they radiate two steady beams, and that's why they're called celestial lighthouses. And only later we came to know they are essentially very small objects which revolve around themselves like Earth revolves around itself. And so they're called neutron stars, which are very uh, compact objects but massive. And so here is, for example, this is a pulsar here, and it's rotating at uh, as I said, two beams here. So how big is it? This is Earth here. This is what's called a white dwarf. It's also a compact object, but not very compact. And but you see a neutron star, barely see that. That's how big it is. And these are some details of what neutron star has got. I will not go into it at the moment. And so this essentially neutron stars happen to be born at the end of the death of big stars. Okay, so now we get to know about pulsars. And okay, look, now this is what a pulsar looks in X-ray. Now this is what's called a light curve. This is in radio. You see, this is actually Crab goes around itself in 33 milliseconds. So this is how it looks in radio, optical. Okay, so but we are after high energy now, so X-ray. See, it's beautiful here. And much more beautiful here is an object, the same object here. Now I will try to show you the next few slides how this is something uh, very great in X-rays because we did see all the detail in optical and radio, and you can actually see the white dot here, which is probably the Crab pulsar. Oh, I should not forget. This is actually came from Chandra observatory, the X-ray observatory, named after the great Chandrasekhar. Uh, the great astrophysicist of the last century, okay, who was of course Indian and worked in Chicago. Okay, so we have now crab X-rays, and we have a wonderful picture also of the crab in X-rays. Okay, X-ray astronomy also has one very great thing that it showed the first ever black hole called Cygnus X-1, a stellar mass black hole, but it's not supermassive as we'll come to know here, but just a star, big star. And this was found in X-rays, and I will not go into the detail here unless we come up with somebody else here. And essentially binary system here, and okay, I'll show here. For example, uh, matter being uh, drawn here and falling on the companion, which or whatever it is, and the That creates the high temperatures good enough for X-rays. Okay, that's called AGN, active galactic nuclei, when this is supermassive. But this one is just a simple star. But how big a star? Okay, it's a very big star. I don't know, it's about 14 something. But this black hole itself is supposed to be 14 solar masses. This is a very recent, last few months estimate. Okay, so Indian effort in X-ray. Though my talk said astrophysics in India, so I thought first I think actually should talk about astrophysics in general and only mention Indian efforts here and there because then it would make more sense. This was the Aryabhatta satellite, and I think the first X-ray payload was put there. And you see, if you can send up balloons up to some altitude, some high energy X-ray work can be done. TFR and some groups did that. So this is how this is one of their payloads. You see this. Please see this plot here. This is number of counts due to photons or whatever, and uh, it's there's nothing here. But when it points out, when the instruments point at this thing, Cygnus X-1, you see a huge increase. And this was a very interesting result, good results of the TFR X-ray group at the time. And this is what black hole, X-ray black holes do. All of a sudden flare up. Uh, they're not regular like what you would expect from a pulsar. Next. Okay, that was in the earlier days, but Indian X-ray community has kept up and also ultraviolet. And 2015, that's why it's almost 6 years ago now. So came up with a satellite called ASTROSAT, which did the multiple the X-rays it looked at, and UV and some other things also. And this has been in the sky thing, and it has done very good work. And I cannot go into all, but again, go back to my obsession here. Crab, for example, here is around the sky around in some units, and you can see this thing. This is what crab looks like in AstroSat. Of course, they have better pictures. And pulsars, if you look, they did the pulsar also, very beautiful here. They have done much more than about polarization, etc. I'm not going to go into that. And so, again, AstroSat, you see, why we keep saying we're doing crab is essentially, as one of my colleagues said, it's like Ganesha for Indians know what Ganesha is. First, you got to look at that. So, only if you can prove that crab seed, only then you can go ahead. So CRAB is a kind of it's a test source, calibration source, whatever you want to call. So this is what many of the experiments do. First, look at CRAB. Okay, so this is X-ray ASTROSAT, and all right, I think I have to go further. It's almost 25 minutes over now. So the next astronomy. The high energy particles. What are the sources? Already we are familiar now. There's a list here. Black holes, we have seen, Farsi, all these are, of course, we had very brief introductions. Active galaxies and pulsars and gamma no, but we can see later. Supernovae and unidentified. Unidentified is interesting because it will flare, it will give only in that particular energy range. So this is the active galactic nuclei. This is a caricature, this thing here. We have a the real one is here. You see this Cygnus A, and you can see two jets, what we call jets here. And the same thing is shown here. Supermassive black hole, supermassive is 10^9 billion solar masses, etc. And this is the interesting jets here. And this is the same accretion disk thing which I told you about. So these are our objects. We know them. Pulsars, active galactic nuclei, etc. In other wavebands too. Okay, now let me go fast. Then next to gamma ray astronomy. The low energy gamma ray astronomy, again, as I pointed out, the difference is essentially The techniques are different. It's low energy, high energy, etc. So this is essentially done with satellites because as you pointed out, low energy, so you got to go up in the atmosphere. And these are some detectors used called scintillation detectors, phase production detectors, things like that. Okay, and one of the first in the 80s was what they call EGRET detector, and this is a historical, agreed, but one got to know that it started out like that, and this is, for example, track of a particle here, and this is the whole instrumentation here. Okay, now the great discovered several pulsars. Now we can see that. Now I had already showed you radio, optical, X-ray. EGRET adds this gamma ray here. This is the gamma ray pulsar, Crab pulsar. The others are there. Let's not worry about it at the moment. So it's looking, look, it is what we call the same phase. Phase is essentially the same part of the pulsar, let us say. And so we have the gamma ray. Also, we have much better pictures with time, but that's different. So we have now Crab I showed you is pulsar also, gamma ray also. Giving there's a pulsar. Okay, I just want to digress here and talk about one small thing. What's called a calorimeter. You see, while we measure particles, no, sorry, we see particles, for example, this is a tracking device. It will just show you the particle, but we got to see its, find out its energy. So we got to make it lose energy in an environment, and that's what's called a calorimeter nowadays. And it's there in almost all high energy and whether physics or astrophysics. And this initially, at least the in a preliminary way, was done by TFR in the late 50s, and in Ooty, it's called a total absorption spectrometer. Essentially, a particle comes, loses all energy. Of course, this energy is sampled out at different places by these scintillators. And so this is what a calorimeter is. And then let's see, if you look, it's huge, humongous. But this is how basically it starts. And it's must in all experiments today. So Fermi, the next satellite, which is still working, for the glass called named after the great Fermi, and uh, this again a calorimeter here. Essentially, what happens, you see, with time different satellites come up. Essentially, the area of the detectors will be bigger. The direction finding would be much better. That's what essentially progress is in these fields. And Fermi was, of course, uh, as we know, the best at the moment. And the Fermi Gamma Ray has given plenty of interesting things to scientists. So I have already showed you some galactic some coordinates, the optical sky and the X-ray sky. Now look, this is the gamma ray. I mean, 30, 40 years ago, this if you had thought at this, there would be barely nothing there. But now it's all populated by different objects. There are the details here. I'm not going to go into it, but pulsars, etc. etc. So this is what progress means. Essentially, fill it up with dots and crosses and whatnot. Here there is a pie graph, but okay, let's not go into that. It says different types of objects found. Okay, pulsars, because we've been talking about it. Gamma ray pulsars are very unique. Really, there are some which are not found in different electromagnetic window. They are the largest class of galactic gamma ray emitters, and they're being studied. To find new pulsars in a totally new electromagnetic window is extremely difficult, but these guys have done that. Okay, because at least the other pulsars, for example, the pulsation periods, things like that. Here you got absolutely no idea, and you got to find that. I think this is a very great work, and so this is the galactic gamma ray pulsars, and also that's so good that even extragalactic, that means outside the galaxy, what gamma ray pulsar is found. Okay, now multi-wavelength crab. Now I think we're putting all this together now. These are the radio. These are what we call false color images, and don't read too much into it at this stage. the colors and things like that, but at least observe uh, the shape and things like that. So radio, already X-rays I showed you, very interesting thing from Chandra. And now gamma ray, you see. So this is what we keep doing. Okay, and this is what's called a spectra. You see, this is astronomy here. This is where physics. You got to understand how many. You got to find out how many photons came and what made these photons. Here, essentially, they're trying to fill in some synchrotron model here, and so it seems to work quite a lot up to X-rays here. Okay, so but still, though, we are. It is like Mount Everest. We are not satisfied. We got to go higher up in our. So what do we do? Okay. Now I come to these fields, cosmic rays and gamma rays, ultra high energy gamma rays, which is essentially what I have been, I was working on for some time. And cosmic rays are charged particles, like what charged particles, protons, etc. Of course, neutrons are also there, photons. They come from different parts of the atmosphere, I mean, sky, here, etc. But they don't cover sky, just go like that. They make particles, enormous number of particles, as you'll see, and so they produce number of particles. They're called air showers. At the moment, don't worry about the names. So plenty of particles are there. So by studying these particles, we know about the original gamma ray, which came from wherever. So most of actually high energy physics, what we call, mesons and things like that, they were detected with the cosmic experiments till 50s and 60s, and a lot of efforts in high energy physics and high energy astrophysics today are successors to those cosmic ray experiments. Now, the interesting thing here is see the energy spectrum. What's the energy spectrum? This is essentially the energy. This is a flux. That means essentially number or some unit time, etc. for some uh, uh, solid angle, like that. So you please see the, I don't know how well you can see it, the X-ray x-axis here. This goes up to 10 to the power 21. So we have all the way from 10 to the power 9, which is a very small energy for this, called 1 GeV. That's a proton mass, and up to 10 to the power 20, which is huge. So we have accelerators in the sky which are producing very, very high energy particles. These, to compare the LHC, that is the one which gave the Higgs boson, Large Hadron Collider, and so on, that they're making energy somewhere here. Okay, and so you see how better nature is doing compared to man. Okay, and so what I'm trying to say really is a lot of work can be done here at these energies when you study cosmic rays and gamma rays, when you study particles which are here. And of course, the rate here it's very, very, very small. Okay, that will come to later. Okay, now the cosmic ray, I told you it comes from different parts of the sky, right? And here, this is real, that's how it comes. But now the problem is they don't point back to source because they're charged particles. What happens is in the galactic magnetic field, interstellar field, etc., they get scattered here and there. So just by looking at cosmic rays, we don't know where they came from. And but cosmic rays also make gamma rays, and because they produce lots of particles, of which gamma rays actually coming from so-called 5 zeros, and so we got to look for gamma rays. This was actually the main motivation for the field in the 60s when it all started out. Gamma ray astronomy as such was a secondary motive. But it slowly, as I said, the astronomy had to be goes up. So it's now people won't worry too much about cosmic ray aspect. It's just very high energy astronomy. That's all. And as I said, they to look at a source in different wavelengths to get a complete picture. You know what the source is doing. What's called multi-wavelength studies. And as I probably pointed out at the very beginning, some sources are there only in high energy bands. So, cosmic what they do is lot of particles now. This is, let's say, from one direction here. Plenty. I'm talking of now plenty means 10,000, 1 lakh, much more like that. This is what actually this is cloud chamber. Why I am showing this is in the lab, and these are all lead dubs or lead plates and steel plates. What happens here is essentially particle comes, interacts lots of particles, and this is what happens in the atmosphere too. And here you are able to contain the whole thing. Atmosphere you don't contain. These are different things to show it goes up in number and comes down because of absorption, things like that. Okay, so two gamma ray fields are really dependent on this phenomenon. The TeV, that's the very high energy gamma rays, and ultra high energy gamma rays, both are dependent on this field, on these cosmic rays here. Okay, he got to know a little about Cherenkov radiation here. Now we all know that light is the light has the uh, uh, highest speed, correct? But that is true only for vacuum. But when it goes through different medium, the velocity decreases. Okay, by n by n is the reflective index, as you'll see in the next slide. And when it happens, then we get what is called Cherenkov radiation because a charged particle also coming in, let us say, but that will have more energy or velocity than the light here. And so then we get what's called Cherenkov radiation, which is basically blue. Oh, this is their nuclear reactor. I don't know who goes near that anyway. So this is the characteristic blue glow here, and that's what is shown. And it happens only if the particle speed is higher. It's called the phase velocity, and it's named after Soviet uh, physics Cherenkov, and some of the theorists Tam and Frank were there. So this is Cherenkov radiation. There is slight more detail here. When the particle comes, let's say from the left, and it starts giving out Cherenkov rays, and this is like a code, and the that is essentially decided by cos theta equals C by VR. So in water, what happens at 41 degrees? It gives out Cherenkov light. This is used a lot in Newton astronomy. This is especially water Cherenkov detectors. And so here, what happens in the air? The particle comes down and it keeps making Cherenkov radiation. And uh, this is the angle with respect to the original. It's about 1.4 degrees. Okay. This depends, of course, on the refractive index of the atmosphere here and there. So what happens is a TeV cosmic rays, TeV is 1000 GeV, the particles actually die out. But what we will see is the Cherenkov radiation is comes through, and that's what we are going to look at. And next 10, 15 minutes, that's what I'll be talking about. Whereas much later, it is the particles themselves can be studied. Okay, so this is what happens when the particle comes here and particle shower, as you see now. Cherenkov radiation comes from all over the place. So there is a huge, there is a big, like a football field or a cricket field, so much that it will be lit up by Cherenkov light. Okay, and in principle, of course, the early days, what mirror it tends to show, it works. Actually, it was found with one mirror in England by Jelly. He was the person who discovered that. But I mean, this is of course very nice now, and this one is what we are going to look at now. The collection area, if you look, this is huge here. As I said, a football field area. Compare it with something in a satellite, which will be just few square meters, correct? So the collection area is huge. You see, that's what it says. Atmospheric Cherenkov technique ACT satellite. Huge. There is only meter squared. And there are several things here. And of course, it's done with mirrors, so it is essentially a nighttime instrument. Okay, so what we do is mirror here, mirror is searchlight, because we don't need very fine mirrors because, as I pointed out, this is Cherenkov radiation come at 1 degree, and it's a spread out thing. So it's okay for us to use not optical telescope quality mirrors. So this is, for example, in the late 60s, TFR group used two mirrors. Now, I mean, looking back, it's naive, but at the same time, it was also very a gallant attempt to find the gamma rays. They just used two detectors here, but naive but gallant. And later at Ooty and Pachmari, we had very many mirrors here. What happens is these mirrors, and let's say what's called a photomultiplier, will sit at the focus of each mirror, and when Cherenkov light falls on this and then gets reflected, uh, the photomultiplier will catch, convert it into signals, etc. So we had 20 mirrors here in the late 70s. Actually, that is when I started this work. Some of my seniors had already begun this work earlier. So this was done by BRC group also in Gulbarg here, and as you can see, we are all talking about high altitude places here. That's necessary because of several things. Okay. Uh, so there was other telescopes. Some were, quite a few were like us, and this was a huge one here, which is a very classic, but also modern in some sense. This is the Whipple telescope. This is in Arizona, and this was eventually it found crab, but much uh, later. And when we started out this work, and I just want to spend a very little time on this, but I have to, how for about 10, 15 years, we were very disappointed many times. But uh, mostly we detected transient emissions and at reasonable pi 6 sigma, that's all, that was enough at the time. Very few what they call gold plated. But I think this is where you got to hand out to the experimenters. Groups were perseverant. So very high energy gamma ray field shut down like that, and it became much bigger and what they call the much better instruments. They call the Mercedes-Benz approach to it, and that's what it is today. So some technique imaging, I'm not going to go deep into it. For example, BARC used. You can see several mirrors here. Like this is done in Gulbarg near Mount Abu. And this essentially shows, this is what's the noise. At the moment, don't worry about what this is. Essentially, how near the source it is. Very near the source, you see a lot of gamma rays. So this is how they detected crab. And we did it a different way in Pachmari, Madhya Pradesh. Plenty of different types of instruments. Okay, now what all finally was done here to get a crab energy spectrum, as I pointed out to you, essentially to show, uh, as I said, this much has been done earlier, but this is what we have added, this part, and the very high energy part. And so how is it understood? I'll come a little later to that. Okay, this is where it is. How are you going to make gamma rays? But means photons, high energy photons. Okay. Now, one way is to what's called Compton scattering, actually what they call inverse, though it's a funny name. And let us say there is high energy electron and a photon comes and they get upscattered. That means they get more high energy, and that's how you get gamma rays. And another way, which is what we really wanted to see, was accelerated protons, like in cosmic rays, and very high energy gamma rays. That means this is a matter target. The pi zero is a very pi zero mesons called, and they give gamma rays. So these are the two competing processes in very high energy gamma rays. And as I will show, or I showed partially, most of the results are understood by this so-called inverse Compton scattering. Oh, crab pulsar was also seen. Crab Nebula I showed, and we have showed in TFR with slightly less significance in these ways. and the magic, which is a super uh, instrument today, and so you can see the two pulses from Crab. Okay, I'm not going to dwell much on that. Okay, now this one plot angular resolution has got to be good if you do astronomy. And in regular astronomy optical, you have arc seconds. Here we have nearly arc minutes, which at the moment is enough for us. And okay, now still one thing we have not done is to you see this is the you can see this is the energy here. These are satellite energies, and this is what we call Cherenkov. So there's a big gap here. So what we wanted to do was to lower the Cherenkov threshold, and so here that means essentially fill up this gap. So there are two ways to do it. This is started in 2000, and build bigger mirrors. The rich people did that, and Magic has, etc. This is Magic Veritas, and they could get signal in few minutes. Now we went to high altitudes, as I'll show you, because when you go up to high altitudes, again the threshold can be lower, and we could do with simpler instruments. Now I remember what Professor Baba used to say, that we should use our resources and whatever we have. That's how we did deep mine experiments in Kolan goldfields, and now we have the highest mountains, isn't it? So we go to high altitudes, and that's what we did. And it was that we went to Hanle in Ladakh. Ladakh, here is the some, I don't know how well you can see this, and this is Leh here, and this red spot here is where our observatory is located. This is the Pangong Lake you heard of uh, quite a lot in the last few months. And Indian Institute of Astrophysics already in 2001-2 they had the optical telescope here on the hill here. And so IIA and the TFR decided to go get together and build the next gamma ray instrument. And this is where this is Hanle village, a beautiful place. And so that's one thing you do. If you do these experiments, you will get to go to places like Ooty, Pachmari, Ladakh. That's an advantage. That's a nice thing we had. And then we built this telescope. Here are the telescopes here. And again, it's essentially the same time, but I know it becomes more complicated in different ways. I'm not going to go into that. And the mirrors are made in BRC, and so we could make mirrors earlier. Earlier days we think they went to Chor Bazaar or Gujari used to call, and they get the searchlight mirrors. But these are all made in India in BRC, and this is one Cherenkov telescope, seven mirrors, and there are seven like that. This is the control room, and most of the time, especially in winter, it's the it's obviously sub-zero temperatures. But the point is, we got to work outside quite often on this, and that's difficult compared to optical telescopes. Okay, so this is what happened. A lot of snow sometimes. And so what happened? This is the height in altitude here. This is so-called energy threshold. Energy threshold essentially means up to what energy you can get gamma rays here. So this is what we had in a place called Pachmari that we did. It's called 800 GeV or something. We could go quite down to about 200, 4 to 5 down. And so this is what we did, and we got interesting results. And I'll just show you one because I keep saying crab, and we did so that it took us some time. Wonderful signal. We got about 20 sigma. Sigma essentially signal to noise, and each year, 2009 to 2017, and 5 gamma rays per minute, whereas all types of junk you get, and that also trigger your instrument. And how this is the signal went up, and also the pulsar. This is not published yet. That's published. We have seen the pulsar quite significant. Some of the results from Hagar, I'm not going to go into that. And so now, again, we have come back to the galactic coordinates here. And see, now we have 200 plus sources here. I don't know, I can't count, but this has about, this is probably, no, this is what I have. And so essentially more and more. And the whole name of the game is to fill this, as I pointed out earlier. And as you have seen already, X-ray had plenty, gamma ray had little less, but TV gamma ray is still less, but it's still a plenty field. Okay, so now, I mean, you see, the thing is, as I said, we went to Hanle, and DRC did with Hanle, our telescopes here are smaller telescopes, but they thought big, they wanted to build something like what the Westerners did. They have built what's called a base telescope, major atmospheric Cherenkov, and this is our Chota Hagar here. They're going to start getting some data this year. They're slightly late. That's underestimate, but we got to be kind. And uh, this is the base thing. This is an advantage compared to many other instruments because we have huge ones there, as I showed you, but they are at the lower altitudes. So this high altitude, maybe we can do much better. So this is good. This I think is all India collaboration at some stage. Okay, much later they're going to have much bigger these things. They're starting up. This is how fields open up. Big telescopes coming all over. They considered Hanle, but for some reason they didn't pick it up. And the progress in this field is, you can see, in 82 we had a small meeting in Uti. Of course, all of these are not necessarily practitioners of the field. There are about 10 of us. These are some foreigners who are doing. There are only four groups. And there are probably some total 20 people in the whole field. But so many years later, it's a huge thing. TV camera astronomy has really made a lot of inroads, and I was not able to talk much about the physics part, but that's where it is. And that's how the field has grown. And but much higher energies, we use the particle detectors themselves because we don't need Cherenkov anymore. These are array 2T, which did a lot of good work. These are KGF, is not there anymore. 2T array now is used for some solar astronomy also. This is something which is. And the Tibet has a wonderful array. You see, this is where going up in altitude. Tibet array is similar to Hanle, this thing. Only these are detect scintillators which look at the sky all the time. And they did wonderful work. And now they have uh, highest energy photon seen ever. This is about 450 TeV. And you can see this is a graph which showed the number of events, etc. And this is how visually it will be. So this is the end actually of photon astronomy. This is probably the maximum one can go to. Uh, Look, the crab, which we keep talking about from the initial days, is still working, and it's the most powerful natural electron accelerator known so far in our galaxy. Okay, now I'm not going to talk about other things because I'm running out of time here. And all I'm going to point out is there are different ways to do these things. Very high energy. This is ultra high energy. This is, uh, it's almost a whole state. We use as detectors. That much area is called Auger, AUGER. That's French for you, Auger. And they have done very interesting work with very high energy cosmic rays. And still, as I'll come to, uh, okay, these are another way to do is neutrino astronomy. Neutrinos, what happens? Cosmic rays, when, as I said, hit targets, they produce lots of particles. Gamma ray is one. Neutrino is another. Gamma ray can get lost. Somewhere something happens, some scatter here and there. But neutrinos come all the way down. Neutrino astronomy is where now a lot of interest is there. And a huge experiment in Antarctica is they're doing. They're okay. They found a lot of neutrinos, but still, nobody can still say we have found a cosmic ray source, whether it's whatever energies it is. Uh, it will take quite some time, I think. So now just to last plot here, and this is the year. This is the number of sources. This is the X-rays. Gone very got you gone out of scale here. It has lakhs of sources now. This is gamma rays. That means the low energy with a satellite. Still okay. It's still somewhere here. Maybe 1,000 sources, something like that. But new instruments will come up. Always that's the way life is. And here with the Cherenkov field, uh, they expect this is, I think they're not found 2020, but anyway, they're somewhere here. And so high energy astrophysics has come a long way, and progress is there in all branches because of perseverance, bigger detectors, etc. Now, the sources, even the old sources are better understood today, apart from finding new sources. And as I said, cosmic ray origin is still an unsettled issue. This is a picture of our HAGAR with snow around. I remember I was there October. It's a very nice thing to see. Early morning you come and see snow there. And in India, for students who would like to do this, essentially the future seems to be in these fields here. X-ray astronomy, as I told you, ASTROSAT is there, and probably I even saw ASTROSAT 2 somewhere in the literature just last few days. And very and ultra high energy gamma ray astronomy. These are the fields which you got to look into if you're interested in high energy astrophysics. Now, I thank Dr. Raplesri again. I've just, as far as I know, just taken 1 full hour. And thank you again for listening to me. Hello?
Oh, I'm sorry. I was speaking all this time, but I was muted. I didn't realize that. I'm sorry. Thank
Okay,
you,
please
Professor
go ahead.
Vishwanath.
Go.
Thank you, Professor Vishwanath, for walking us through these very high energies in the cosmos. And I was just mentioning that participants could type in their questions in the YouTube chat window now. And there were some earlier questions too. And before I,
Can you read? Yeah, I
yes,
don't know how to
yes,
look
I
at
will.
it.
I will. Yeah. I'm just trying to pick them up, and yeah, just I'm just going through. There was a question from Hemant Kumar: does singularity exist at the heart of black hole? That was his question. Hemant Kumar: singularities and
What
black
was the
holes.
thing?
Does singularity exist at
Similarity.
heart
I'm
of
sorry, I'm not able to.
yeah
Okay,
singularity
I know.
at the heart of black hole?
Uh, no, you see, I'm not the person to be answering that, if at all. So I do. We study. I'm an experimentalist, and I cannot, with any competence, argue about whether there is a singularity or not. Okay, we try to study black holes, and I think maybe 1 or 2 results I showed. So I'm sorry, I cannot answer that question.
Yeah,
Okay.
students do always come up about black holes. First of all, that is
No,
what
no,
they
very good,
do.
very good, very good, sir.
Yes,
But
yes.
I'm not confident that.
He was also asking. Hemant was also asking about Higgs boson and so on. From what
Yeah.
is, I mean, he was asking what is God particle. I told him to rephrase it as what is Higgs boson, and he says he wants to know why that is.
Well,
I'll
Higgs
give
boson.
a
I
yes,
don't know
please.
whether I should say, but anyway, little because this is astrophysics supposed to. Higgs boson, as far as I know, is something which the Higgs field is something which gives each particle a mass. Okay, and the Higgs boson is, I forget what, 140 degrees, something like that, or 20 or something like that. That's what the LHC has found. And the idea is I mean, I also pick it up just like you from popular this thing. So, like, it's a slush field, and how fast the particles go through. And for example, photons supposed to go through fast, so photon has low mass, whereas a higher mass thing like a top quark or something will struggle through the slush and get all that slush, and so it gets mass. So that's all I can tell you.
There was someone who was very excited by these topics, and he was also asking whether he could uh, make some inputs of his through animations and so on. I'm just trying to find where. Yeah, Amrut Desaraju was saying that he interested in animation about natural phenomena like nebula and so on. I told him to go ahead and learn the science and do the animations, and then maybe
Yeah,
approach planetaria and science centers who would find a lot of use for that.
yeah, that's
Now I
true.
think some fresh questions are coming in. There was also
Oh,
one comment, and I actually just did want to mention an answer to that comment too. Sudarshan N was mentioning that these are such interesting topics, but many people don't know about these lecture sessions, and he was asking us to do something about it. Actually, we do send to about a few thousand school and college teachers and ask them to pass it on to students and also directly to students through various groups. Maybe these are exam times and so on, and maybe that is what, maybe lower presence. But I think questions are coming in now, so mostly from students who get excited by these very esoteric topics. So Sachin Pandey wants to know, fabric of space time made of.
so you should, Dr. Ratashri should have the talks to answer some of those questions. This is,
Yeah.
uh, I
Yes, yes,
really, yeah,
yes, yes. I know. Somehow,
maybe
I mean,
somebody, maybe somebody in the audience can answer. I don't know. Yeah,
yes.
fabric of
Usually,
space. Okay,
we do have a number of college students who come in who have specific interest in what the topics which are going, and we get a lot of good questions from college students. I do not know whether these are exam times or what, and so we I do not see the ones who are very regular and have such good questions,
right.
and but it is possible that we may pick up a lot of viewership later on, because sometimes also there is, Professor Vishwanath, what is happening is that our being so close to the National Science Day, there are a number of events ongoing these last couple of days or so. So we may also
Uh-huh.
have
Oh,
got our viewership split a little because of that, which would mean that they may come later on to look at it. And then if there are questions on the YouTube channel
yeah,
itself,
yeah. Please,
I
please.
will
Yeah,
pass them on to you. And
yeah, sure.
if there are any further questions anyone would like to ask, specific also to what was spoken today. So I actually wanted to ask Professor Vishnath that the crab one, the full multivalent spectrum that you showed, where it is falling down and then the very high energies are picking up. We probably don't have such a wide view for any other object, perhaps. But
No,
do we
no,
have
no.
any?
Actually,
Hmm.
yeah, no. Actually, that's why crab is so special. Okay, and there are, for example, you do get some total energy spectrum for things like Mercury 451, 501. These are blazars. Okay, I did not show some of those pictures, so you can get some of those whole from radio onward to very high energy gamma ray. Okay, but I think crab is special in the sense I even went up to 450 TeV. Okay, I don't think any object has been studied at all, and I'm sure with time people will do it. For example, Tycho, Supernovae, etc. They have been seen in gamma rays and things like that. But crab is the only one, I think. That's to some extent what they are stressing. And it's not just both qualitatively and quantitatively. It's the best studied source, and with time maybe we'll get something else. But today that is the only one.
I was wondering whether, I mean, just in a narrower maybe window, but which captures both the fall from the earlier energies and the rise to the very high energies. Specific to pulsars and
Yes.
supernova remnant like objects, we don't have any other example. Just this
Uh,
part at
I
least.
don't know. Yeah, no, I'm not sure Tycho whether we have Tycho supernovae. That part I don't remember. What happens there, the fall at the higher increase you saw, essentially the two phenomena, the higher one, the inverse Compton scattering takes over, and in the lower one, it is the synchrotron radiation. This keeps happening, I'm sure, in all many of these objects. I think you said 1006, that's the lupus supernova, something like that. I think it happens there also. But so uh, so it happens in many of these things, but as I keep telling, the whole thing, as they call the enchilada, from beginning to very, very end, I think it's the only crap.
Amritanshu Vajpayee has a question about jets in AGNs or X-ray
Yes.
binaries. He wants to know whether they are electron positron or there are other baryonic
Well,
particles in
the
these.
thing, you see, I think there have been several uh, theories here, and I have seen, for example, in AGNs, uh, this of course is we see here, uh, they talk about different cascades, things like that. Okay, of course you have got to will get electron, proton, also proton. This thing, this actually they call a proton cascade. Some people call. Okay, just like in a calorimeter or something, experimental which is shown. So I do not think that it is totally well understood, except as I showed you in AGMs here. Uh, they try to fit different, our own people in IIA have done that. 1 minute, let me try to. This is a particular region here called market 451. Oh, here. You see, for example, they try to fit this sparse number of points here. This is an this is a spectrum here. So here, the thing is, this is the inverse Compton here, and this is your synchrotron, less like in Cramer somewhere. And so at the moment, they say that this fits better, but there have been some other plots I've seen that they try to fit protons cascade in a proton interactions, and they don't fit that well. So at the moment, this is what is happening. So you need, of course, high energy electrons here for inverse scatter, and that is what is happening here.
Thank you. In your last
So we
slide,
don't have very
the
many. Which slide?
sorry, I could not hear. The last slide, there was that graph showing discoveries, and there was for one of them there was a small plateau at one point. Uh, the last slide which showed the Kifun curve or something like that it was called.
Ikude. So that's a gentleman who went on producing that. And
Uh,
yeah,
so there was a
here,
small plateau there. So was that there was some period of
one
time
minute.
when there were no space? I mean, no spacecraft looking into these energies. That little bit of plateau which was there.
Here. Uh, why am I missing that? Sorry, one minute. I think this is the beginning teething problems with our webinar.
Yes. Yes.
Here.
Yes. Yes.
Now
Yes. Yeah.
you're
Yeah.
talking of some plateau
Middle
here,
curve.
if I'm
Yeah.
not
The middle
mistaken.
curve. Yes. Yes.
Somewhere
Yes.
here. I don't, yeah. You see, that the thing is, for example, here, these are the low energy gamma ray satellites at different times, as2, Cosby, EGRET, etc. And so I think it's essentially a question of money and time, energy, etc. Typically
Mhm.
15, 20 years between these, okay. But here you can see it's probably much more, okay. And so I think it depends on probably the amount of interest in the field and also also the energy one has to start doing new experiments. I think that's what probably decides this how fast these curves go.
Thank you. Sachin Pandey, your question about drilling a hole nearly to core of Earth, etc., ocean draining into it is a little off topic, so we are not taking it up. And perhaps if there is some related
Which one?
talk. Sachin Pandey
What is
wanted to
that?
know about if you drilled a hole nearly to the core of the Earth and did it in the ocean, what would happen? Would the ocean start draining into the hole? So not directly connected. So I was telling him that we'll pass that for now. And yeah, I
This is, I
see.
just want to show you one thing.
Oh,
Whoever this
sorry.
here, you see, for example, in Antarctica here, these experiments called Amanda, of course later Ice Cube,
Sorry.
they kilometer down here, they put detectors. The thing is, for example, they had to drill holes here in the ice. They do it with hot water, jet. They immediately put the instruments. No, I know what I'm saying is probably not what you're asking, but I'm just telling you, drilling a hole here in ice. Okay. Okay. Next.
Uh, Sorry, I actually could not. I don't know whether the problem was mine or whether the people could hear it. I could not quite hear that fully. And there
Sure.
is one other question too about possible models for interaction between matter and dark matter. Amritanshu Vajpayee.
Yeah.
And
Yeah. Okay.
once again, not quite on topic, but if
Yeah.
you
Dark
wish to take,
matter. You know,
I,
there are some
uh, uh,
experiments to set up limits. But I don't
yes,
know how
yes,
well.
yes, yes, yes. All, I think now I don't see further questions. And thank you so much for once again, as I was
Okay.
saying, for walking us through these very, very high energies. And I just wanted to ask one question last, if it's okay, that the objects that we are looking at through this are usually, I mean, typically pulsars and then quasars, blazars, and those kind of objects, and maybe supernovae. And
Yeah.
so this makes the kind of full set of objects that we are looking at through these.
Yeah. No, like I told you, gamma ray bursts, things like that.
Uh-huh,
Okay.
Which are
There
still
are the
related
gamma
to
ray bursts.
these kind of objects.
Yeah, I see. Because you need quote unquote some violent phenomena, no, to like non-Lucas
Hmm.
violent phenomena in you, because there is we don't have thermonuclear reactions here, so we need something else powering up all this, and so it can so that's how your X-ray astronomy etc. opened up because these were possible, correct? So here is it. Okay, I think I've got it here. Ah, here. I see, for example, here sources of gamma ray emission: black holes, AGNs, pulsars, gamma ray bursts. Diffuse emission is
Yes,
also studied, and
yes.
supernovae. Yeah, these are all, as you know, points out to the end stages of stars, correct? And that's because that much energy is possible only in those processes.
Thank you. One of the
For
viewers.
example, yeah,
Yes, please. No, I interrupted you. I was just saying that one of the viewers is happy with the session and says it is very energetic. Pun intended, perhaps.
probably,
So,
probably. No, it is, what I wanted to say. For example, sun is a X-ray emitter, but a marginal level. So stars are
hmm,
not great X-ray emitters. Okay.
hmm, hmm,
Yeah.
hmm, hmm. Thank you so much once again, and thank you for all the viewers who are there. And I am ending the broadcast if I don't see further questions. And so, once again,